let's start our lecture today. First, I would like say thank you to Dr. Watanabe. He's an expert for the Muon spin relaxation spectroscopy. He's from RIKEN Nisina Center for Accelerator-Based Science, Muon Science Laboratory. I know Dr. Watanabe since I was in PhD students a long time ago, maybe 15, 2023, now 2021, yes, more than 15 years ago. So we have a quite a close collaboration between UNPAD, especially some Indonesian researcher with Dr. Watanabe. Dr. Watanabe also the professor in Hokkaido University, and also become a guest professor in University of Indonesia. Okay, today we are very glad here can invite Dr. Watanabe to give us a very valuable lecture. Actually, this is the one of the lecture in magister program in Faculty of Mathematics and Natural Science, University Pajajaran. The lecture actually, the name of lecture actually crystallography and spectroscopy. And here we invite Dr. Risa Watanabe to give one of the thema in our lecture, especially for the Muon spin relaxation spectroscopy. I also invite our college from UI, ITB, UG, UGM, ITS, and from Indonesian Magnetic Society. I think one of the participants is also from the society to attend the lecture from Dr. Watanabe. Okay, I think we have quite enough time. We can discuss about Muon spin relaxation USR for investigating magnetic properties of material. Actually, we have 2.5 hour, quite long, a long term for lecture actually, but hopefully you can discuss with Dr. Watanabe a lot of things here about the MUSR spectroscopy, and also I think during the lecture, if you have some question, you can also raise your hand and ask directly to Dr. Watanabe. I mean, it is not necessary to wait until the end of the lecture to take a question. So it's maybe easier way. Or you can put your question in the chat room, in the chat box, so we can. So also Dr. Watanabe can also see the question. Okay, let's start our lecture dengan menyebut Bismillahirrahmanirrahim. Bismillahirrahmanirrahim. Okay, Dr. Watanabe, time is yours.
Thank you for introducing me, Professor Disdiana. Nice to meet you. Morning, all of you. So I think all of you are still fine, and I'm also fine. So then I'm going to talk about my specialty, which is the Muon science, to all of you. So Professor Risudi, he was working with me for a long time, just like more than 3-4 years in Japan, then studied about the Muon science with me. So then my basement is not in Japan at this moment. So my office is in Japan, RIKEN now here. But my basement is in the UK, Britain. By the way, how is the sound? Is it okay?
Yes, it's okay. It's pretty clear.
Okay.
Yes.
So then I have been working in the UK on the Muon science there nearly 30 years, maybe the before almost of you were born. So then today, what what I want to do is, I heard from Professor Diana, some of you were attending to the Sakura Science program communication in February, but some of you, maybe the first time to talk and to meet with me. So then in the beginning, luckily I have 2 hours today. Luckily I have 2 hours. So then in the beginning, I introduced myself to all of you. Then they come into the research talk. Then 1 week or 2 weeks later, this week,
Yes.
I have another one.
Yeah.
So then,
Yeah.
due to some the busier time now, so I'm now negotiating with Professor Diana to postpone my talk to be in the beginning of the April, because this week, next week, is a little bit tougher week for me. But I don't know whether he allows me or not.
Yeah. Okay. No problem.
So then maybe how is it English?
Yes.
Is great. So if my English is not so easy for you to hear, so could you please stop my talk? If you say excuse me or something, and hands up, maybe okay in the chat, then I can stop at any time. So for instance, not so easy for me to talk continuously for 2 hours. Then if you can disturb and have question to me during my talk, it's easier for me to consume the time. Okay, so then I'm going to share my screen. これか？どうですか？これで OK ですか？
Yeah. Yes. No. Yes.
What?
Okay. This.
Wait. OK。それでなんだっけこれ、ポインターどうやんだっけなこれかレーザーポインター。
Yeah.
これだ。Okay, so this is a snapshot of the last month. In the last month, during we are carrying out the Sakura Science Program communication. So then we've got the photographs here. So that we enjoyed nearly 10 days to discuss the superconducting states measured by the squid machine in Riken. So then this time, due to the COVID situation, nobody couldn't come to Japan to enjoy the squid measurement by themselves, unfortunately. But just I've got a message from the JST, which is Southern Science Program Office, this week. They are going to manage to invite all of you as much as possible. Then I required to invite you maybe after June or July. Maybe following the business track arrangement, if the Japanese government allows you to come in on the basis of business track, maybe all of you can come in and enjoy the communication. So then this is not the last one, okay? This is the first one, just the beginning. So then I continue to work with Professor Listiana. Then they invite some of you as much as possible to see what is the Japanese scientific situation, and also to enjoy the talking with my Indonesian students. For instance, this lady, the Utami-san, she's attending here now. So she's in my team member in Riken and working on a pilot claw, the assistance by using many techniques, just like X-ray, squid, resistivity, and blah blah blah. So then she's like you. She was like you. So she just joined to me from the PhD course. So then still enjoying the science. So what I want to ask all of you is, during this event, so just please think, you can have possibility. You can have a possibility to enjoy more sciences even in the world, no problem. As long as you hope, then you can open your way to go outside and enjoy the science. So please understand. So then, but in order to do, it's not so easy. For instance, you have to use English like us and others. Then if you, but I think lots of people said to me, my English is too hard, quite hard, like a solid like the sound, so not so easy to hear. So then, but you have to communicate with like that, with a person like that. So then, at any time, please stop the my talk and hands up and ask questions, or you can ask like that. So could you please repeat again? I couldn't hear. It's no problem. Okay. So then I graduated from Hokkaido University. Hokkaido University is one of the 7 imperial colleges in Japan. It's like a top 7 universities, luckily. Then that is in Hokkaido. It's the north part of Japan. So these are my old photographs. So I'm here, and this is my here, and this is me, and also I was somewhere around here. So then I enjoy the physics by using the nuclear magnetic resonance, not MSR. So in parallel with the NMR study on the high TC, I also carried out the MSR, both together. Then after graduation, I moved out from the NMR field and moved into the MSR world. Luckily, MSR and NMR both together are very closer. Then from my viewpoint, it was not so difficult to join the MSR field by using the NMR knowledge. So this one, these are my our laboratory members, the all 7. They had the motorbikes by their own. So sometimes we went out to enjoy the driving and talking, and sometimes we have to go to attend the Japanese Physical Society meeting twice per year. Then we always use the motorbikes to go out from Hokkaido and come into the meeting places. Sometimes I drove the motorbike more than 1,000 kilometers per day to enjoy the driving and watching the sightseeing. So this was a quite good experience for me because at this moment I had to travel to the UK and many other places, just like Indonesia, Malaysia, Taiwan, and the US and any other places. So then when I was in the university, I began to like such a long time traveling. So then it's not so difficult for me to travel in the long haul, but now it's quite enjoyable. But unfortunately, at this moment, I cannot travel to anywhere. So this one is just like a presentation style. So 30 years ago, so the presentation style is completely different from now. So some students who are working with me, they can understand how different the presentation style is from the current one. And also, when I was in the university, we used the OHPC and overhead projector to present our oral talk. But now we can use a PowerPoint files or Keynote file like this. Then everybody in the world can share my talk. It's quite amazing. So then my basement, I'm now here, in Riken. They're very close to Tokyo. So this one is a WACO main campus, the Riken, we say Rika Kenkyujo. So then this one is a Nishina Center, where we are using the accelerator for the nuclear science. But I'm not a nuclear scientist. I'm the solid state physics, but belongs to this center because technically we use the accelerator, which is similar with here. So I'm around here. This is the main building. So at the west end, my office is here on the 3rd floor. So then they're very close to Tokyo. So then if you come to the Riken, you can understand how easy you can access to the center of Tokyo. For instance, Shibuya, Ikebukuro, Shinjuku, Harajuku, Akihabara, anywhere you can go access from the Wako city by using the underground only, like in an hour. So my university was here, Hokkaido. Distance is around 800 kilometers, nearly 800 kilometers. So that means Japan is quite long. just like a Java Island. So Java Island length is just around 1,000 kilometers, I think. So from here, from Sapporo to Tokyo, nearly 800 kilometers. So the 1,000 kilometers range is from here to Osaka, around. So Java Island is like that, but Japan mainland is much more wider and very, very narrow. So then from here, I'm not talking. So this one is a photograph in the spring season. I took the similar photographs, the Wako campus, the cherry blossom, the photograph, but I couldn't have a time to prepare to show the recent photographs on my screen. I'm sorry about this. But now the season is full the cherry blossom. So we can enjoy this very beautiful view. However, the cherry blossom lifetime is very short, like 1 week or less than 10 days. So today is 2 days ago, we've got the announcement of full cherry blossom in Tokyo area. So then maybe these flower leaves will disappear within a week, just like at the end of this week, maybe all the flower leaves will go. So this is a typical sakura cherry blossom. So please, the image, if you are in Riken, you can see this one in every April. So Riken is now quite big national institute in Japan. There are 3 biggest National Institute for Material Science in Japan: NIMS, ICE, and Riken. And also Riken has some centers within Japan, and all other centers outside Japan, just like Beijing and Singapore and the US and the UK. So I think you heard about the name of the supercomputing system K, but now is a Fugaku. This one is in here. So last week we went to here to see the Fugaku for another science program. So now we are now in here. So here is a basement to use the muons to work on the material science by using muon. Okay, here is the Rutherford Appleton Laboratory in the UK. So this was one of the biggest, the National Institute for the Science in the UK. So the Rutherford Appleton Laboratory itself is just around this area, So this one is my basement. So I have to go here so frequently, and also my students, they have to go here so frequently. So here is the radiation synchrotron source named Diamond. This one is not a part of Rutherford Appleton Laboratory, but now they are now forming the research complex in this area. So here is a Howell laboratory area. This is basically for nuclear power source plant. But now there are many small companies who are working for the the development and technologies of nuclear power plant. So nowadays they declared this area to be a Howell research complex. So the Rutherford is a part of them now. And Rutherford, you can see just like a round shape here. This one is also an accelerator which has the strongest, which can deliver the strongest muon and neutron beam in the world. At this moment, the JPAG in the Tsukuba is now growing up, and the quality is nearly the same. But in total, the quality at Rutherford is #1 this moment. So here is the synchrotron accelerator like this. This one is an electron synchrotron accelerator. This one is a proton synchrotron accelerator. So then the beam is very strong, the worldwide strong. So then we can kill any person by using this beam. So we are already working in this building, which one is the experimental hall. So this one is a Rutherford, the Riken Muon facility, which we built up about 30 years ago. So this one is a real of my basement, then to carry out the muon science. So many the small things there. Then there are 4 ports here, here, and here, and here. Then I joined Riken in 1992 to start up the construction works of this facility. So then I was in charge of the real construction at the site. So then for about 2 years, we were concentrating in the construction job. It's not the science, just the construction. So then we have to talk with the engineers and local people and managers to proceed this construction job. Then before I joined to Riken, I've never been to abroad. I've never been to have my passport. I've never been to spoken any English. So then just after I joined, in the same month, it's April, I had to go to the Rutherford here to start to work on the constructions. Then I had to remember the English. Then now my English, I didn't study the English so much. I didn't like the English. My score in high school was very bad. Maybe I was very surprised because some of you they can speak English so frequently, even though you are in a bachelor and master course. They are comparing with my age. It was very, very impressive because in my master course age, I didn't say anything in English, but you can speak English so very well. It's a kind of wonderful situation. So the Indonesia is now opening to the world. So maybe the distance to the world for you is much closer than my case. So please think if you want to enjoy the science and the worldwide conditions at any time, please talk to me or my students. Then they can show and I can show you how to join and how to try to enjoy the new field. Then we started from 1992. Here, this is me. So I understood the nuclear physics technology. This is completely not a solid state physics technology. This is completely nuclear science and particle science technology. Then everything was quite new for me. Then I had to study the many technical things so much. Then I did the constructions with the Rutherford engineers and my colleagues. Then we got the first Muon beam in 1994, November. Then after that, we have been continuing the Muon science with many collaborators. So because this seems quite expensive. Sometimes I talk about the price or cost of the equipment. So these are covered by Japanese taxes. So then what we have to do to return back these costs is to give the benefit to the collaborators and the users, to the Japanese and the worldwide citizens. So that was my duty and still there. Then what we did is to collaborate, to make collaborations, so many in the world. Okay, see here, I'm here. I was in charge of this, in charge of this, and in charge of this. And blue magnet, I helped to design and installation at the site. Then I stayed in the UK for nearly 2 years, then leading this construction. So then we got the ceremony like that. This one is the previous Ricken's president. He's passed away 2 months ago, unfortunately. Then we renewed the MOU time by time. Then still we are continuing to work with Rutherford more than 30 years. It's quite rare why we can continue the 30 years collaboration, international collaboration for Japanese groups. It's very rare, the cases. So the rare cases means how successful our project is with the UK. So then you can enjoy the talking with the UK person so much. But recently, due to because our facility have become very, very old, and also the recent situation doesn't allow us to continue the facility operation by Riken only. So then we are now operating the Rutherford Riken Lamine facility. We see the Rutherford, the main body, themselves. So then we say cooperation, but still the Japanese and worldwide Riken users can enjoy the Muon science with us in the UK. So this is very old information. Very old information. So at this moment, we've got many big record to have many visitors, and now we have we have, how can I say, nearly 1,000, more than 1,000 researchers and visitors to our facility, and we've got nearly 500 papers published in the past on the basis of the regular Muon science. So including nature, science, and physical laboratory, physical and level B. So then we're always trying to publish our studies in the high score the good journals. For instance, Professor Lee is here. So he was working with us, studying muon science. Then this is the reason why I'm now talking to you, and also you are hearing my talk. So this is very old photograph. And some of the researchers in here, the Professor Goto and my colleagues, and also Ai-san and other people, they are now still working in the research field with us, carrying out their own research. So then I've got some students like that. So here is a Dita, Dita Spitasari. She graduated from the ETS, and joined to us. But still, she's got a job in the near Japanese university here, from near here. Then she's still working with me. She's in the JPAC now, carrying out some muon experiments. So then I hope some of you can chase her and join to us to enjoy the muon science. Okay, so then sometimes I can say like that. So the guy, they joined to the muon scientific field. There is a very interesting the legend, the effect, the muon irradiation effect. So they used to be, I had the very good, the hair like that, but now I had completely lost my hair like this. So interestingly, the researchers who are supporting the muon science in Japan, they all lose the hairs like that, beside the muon irradiation effect. So then the ladies are fine, but the guys, be careful. Okay, so then これ、リスイ君どうやって止めるんだ So then, I'm going to move to the now real scientific part, okay? So rest of that, I talk maybe tomorrow because I have more time the next time. I'm not sharing the screen. Oi, could you please somebody?
Yes, yes.
Can you see?
Yes,
Okay.
still same slide.
Okay.
Okay.
Let's move on to the scientific part. So just simple introduction. So then what I'm going to talk about is what is the muon science. But if you talk about the muon science in detail, I still use nearly a week.
Sorry,
Then when
I think your slide is still domestic international collaboration, not yet the.
I see.
Yeah.
これで
Not yet.
どうだ
Okay.
How is it?
Okay.
Okay.
Yes.
37 people now attending. All right, second.
Yes.
Majority of students are in a master course or undergraduate?
Master course.
Master course. I
Yes.
see. First year.
First year. Yes, first year.
First year. So you have 2 years master course, okay?
Yes, yes, right.
I see. So then after master course, you can join to the companies and the societies, of course, but you can join the PhD course to enjoy the science, which is, of course, not so easy, but quite enjoyable. So, okay, come back to the scientific talk. From now on, what I'm going to talk about is I talk about the basic knowledge of what is MUSR, how we can understand the MUSR study. So then if I speak one by one, that becomes very complicated and not so easy to chase for young students. So then I picked up the topics only. Then they talk about the basic knowledge. Then as long as you understand this basic knowledge, maybe not so difficult for you to discuss and to see the MUSR results. So I don't use so much the difficult conditions. So could you please understand much more simply how please recognize how easy the MUSR is to understand and to discuss the physics. Okay, come back to the Rutherford Appleton laboratory. So if you see the top view here, あれこれはこうか。Top view and here, nothing. Okay, UK has a very flat land. So the highest position is just less than the 2,000 meters. So the very flat. So if you come to Rutherford, and here is like a hill. So if you stand here, you can see it's just like the border between the sky and the land. Landscape you can see. Okay, if the weather is fine, you can enjoy a very amazing view. In UNPAD Depok, not Depok, like Jatinangor, is surrounded by mountain areas. Is it true? I stayed in the Begege, just beside the UNPAD, a long time ago. From there, the view is very wonderful, very flat. But on the other hand, to the Bandung direction, we can see many mountains surrounded by mountains like Japan. But UK, almost there is no almost a higher mountain, so then you can see a very flat view and covered by just like a rice field and the sea field and cow fields. Okay, so Muon. What is a Muon? So Muon is basically not for solid state physicists. So this one is a fine particle. So then usually we discuss a muon in the field of the particle science, the high energy particle science. Because why muon became the important and famous is the Japanese, the particle solution, he's a Yukawa. He's the first Nobel winner in Japan, and he predicted the nuclear power force, mediated by the muon. Then the muon was found after that. Then this becomes much more famous in the world, scientific world. Before that, nobody knew about the muon. But now we can use this muon for the material science. So what I want to say is, you don't need to know about the detail of the muon itself. As long as we can know about the simple characters of muon itself, we can use muons for material science. So then where's muon? That's a good question. So then at this moment, even in Indonesia, you must feel the muons. That is, if you open your hand, the 1 muon is passing through your body per second. So that means you should feel muons, but of course, muon is a fine particle. You cannot see, you cannot feel. But actually, the muon, 1 muon per second is passing through your body. So from where such kind of muon is coming in, that is we say the cosmic muon. That means the muon is originated from the cosmic particle. So this is Earth, and Earth of course has the air. So then the cosmic particle, that means the cosmic charged particle, which was accelerated by galaxies up to the 99.999% light speed. So in the space, there are many such kind of the accelerated charged particle. So such accelerated charged particle hits the air like that and produce muon. So then this kind of behavior is naturally ongoing. Then from the beginning of the Earth or the air, even in the dinosaur stage, the muons are still there. At this moment, still there. You should feel these kind of muons, cosmic muons. So then recently, we use this, not we, some researchers, they can use these cosmic muons to judge inside of the volcano. So this one is Professor Tanaka in the University of Tokyo. He used to be the postdoc to us. So then he found the possibility to use this cosmic muon to see the inside of the volcano. So what they do is they put the muon counters near the mountain, but the cosmic muon has a very high energy, so can pass through the mountain so easy. The cosmic muon, comes from the space and hits the mountain, passes the mountain, and detected by the counters. So then if the 1 muon can pass through detector 1, detector 2, and we can understand the position. So that means from where muon is coming in. That can be the understood. Then making a statistics, because only 1 muon can come in per second, so then we need a half of a year to gather the realistic data. Then putting these counters for half a year near the mountain, then they observe the mountain area from the 2 directions. Then we use the statistics, then they making the image of the inside of the volcano. So this is a realistic view, the photographs. This is the real activity to see the volcano by using muons, led by the Professor Tanaka. Then this is the solar panel to produce electricity to the counter. These are counters. Then they located this one near the mountain, then wait for more than half a year, nearly 1 year. Then they, due to the Wi-Fi network, it's a radiated network, we can see the data from here on time, day by day, no problem. So thanks to the decent technology for the Wi-Fi. Then this is the image. So inside, this is a mountain image. So here, the white one is a dilute one. So black one is a dense one. Dense one means a lot of rocks are condensed here. But here, the density of rocks becomes very less. That means the magma tranchunda, the melted rocks are coming up from this area. So then if you see some the melted rocks are coming up, that we can predict when the volcano is erupts. So then this is the now they become the quite good the research field to predict the volcano eruption. Then this one is 3D view. So of the such a sort of path through the path for the melted rocks like that. So if you're interested in this kind of the research area, of course, you can contact with the University of Tokyo, Professor Tanaka. He's young, so then he also has, he's still continuing this kind of job, so then you can join. So the triggered by this study, nowadays the muon is being applied to see the inside the pyramid. So this one is on Nature, the news, released in 2017 or 1917. Then we are very shocked because the muon was used, can be used to see the inside of the pyramid. This is the pyramid for King Khufu. So this one, the national treasure Egypt, so that we cannot come in so easily. But by using muons, we can see inside and investigate what are there inside the pyramid of King Khufu. This one is quite shocking, the news. Then there were some the TV programs to release the news of this. So this is a very famous, the newspapers, the copy, Asahi newspaper. This one is the major, the famous, the newspaper in Japan. So then in Egypt, they try to see the inside Khufu pyramid, King Khufu. Then by using muon. Then what's happened is, this is how to see if there are some empty spaces inside the pyramid, then we can see more muons which are passing through this empty area. So these are cosmic muons. So then the result was, so this is how to work in the pyramid. So these are students from Nagoya University. They went to there and allocate. These are counters, muon counters inside the pyramid. Then they put the nearly 1,000 counters, as long as I remember, in the pyramid and gather the statistics. So this is a laser level meter. So then they allocate the muon counter so carefully. This is another muon counter. They allocate in the pyramid, King Khufu. So these are team members of this project. This was released in the Nature, the journal. So then what's happened is, these are well-known, the King's Room and the Queen's Room. A Queen's Room here and a King's Room here. But in the end, what's happened is they found another bigger area just near or above the queen's room. So unluckily at this moment, we don't find out any the mummies in the king room, neither in the king room nor queen's room. So then they are now exciting. This could be a realistic king room that we could see the mummies in here. So then the investigation is still going on because the number of the cosmic muons are very less. So then they need a long time to gather the statistics. But now this was a quite good evidence that how we can use a muon to transparent the solid body. So then maybe the news will be released in a couple of years, and maybe we can enjoy how to use the muons, the new science. Okay, come back to the muon science. Now it's I'm talking about the solid state the condition. So the muon, as I talked to you, muon is like a fine particle, but you don't need to know about the detail of the muon character. What I needed to remember for us is this, just only this. So mass is very light compared to the proton. The proton mass is quite heavy, but the muon's mass is 1/9 of the proton. It's quite light. Then we can say light proton. On the other hand, the muon's mass is quite heavier than the electron. The electron is also the quite light mass, but the mass of the muon is 200 times the heavier than the electron. So this one is very important character because the muon's character in the mass is in between proton and electron. And also next important character is the muon has a charge, both positive and negative. So these are important. We are now using both, but for different purposes. But mainly for solid state physics, we use positive muon. Positive muon is mu plus. And the charge condition is the same with the proton. That means the charge volume is the same. The negative condition is the same with electron. So that means the proton, muon plus has the same character with the proton, but with a lighter mass. On the other hand, negative muon, that mu minus, has the same character with electron, however, heavier mass. This is the important characters, the old muon. And also muon has a lifetime. Muon cannot exist forever, like a proton and electron. That means the muon has a lifetime. The lifetime was not so bad. It's not so bad, just at 2.2 microseconds. So if you say 2 microseconds, that seems to be quite short. But this is quite good enough for material science. For instance, like a pion, that is another fine particle that has only the picosecond or nanosecond lifetime. It's very short, too short to observe. So then the 2.2 microsecond can be the useful for material science. Then we chose the muon. And also muon has a spin, half. Spin half means the same with the proton. That means the muon can be used as a magnetic probe. You know, the NMR CT scan, I think I don't have any photographs here. So the NMR CT scan, they use a nuclear magnetic resonance of the proton inside the body to see the inside the body, okay? The NMR CT scan, maybe the some of are there. This second, does UNPAD has the NMR CT scan system in a medical section?
Yes, of course.
Oh, good.
We have in the hospital.
In a hospital, yes.
Yes.
That are very important, not to give any damage on the body, but to see the inside of the body. Very important recently. So then that uses the NMR, the technique, the nuclear magnetic resonance technique of the proton itself. Proton is a part of water. Then the human body contains 70% of water. Then we can cut off the body by using NMR to see the inside. The same thing we can do by using muon if we forget about the muon lifetime. But the muon can be used for the magnetic probe, just like we can do the similar experiment like NMR. So then always I can say to other people, the muon is a part of NMR. Then the techniques and principles are all the same. So but however, the biggest problem is muon is available from the from the space, only 1 particle per second. This is too small. that we cannot detect, we cannot have any statistics by using such a sort of the small numbers muons. Then the researchers, we cannot use such kind of the small numbers, so the researchers, they constructed the accelerator to produce muon artificially. So then we say the accelerator physics. But not only muon, but also other particles can be created by the accelerator. So Rutherford Appleton Laboratory is basically for the neutron science. So then the neutron are available in this facility, and also muon is also available in this facility at the same time. So then we have to use the accelerator to carry out the realistic material science. Okay, how do we have the muons? Let's see. So this is the image. So if you talk about how we can have the muons mathematically, it's impossible, completely impossible for me, because there are many difficult equations to be solved out. But unfortunately, we don't need such a difficult knowledge, just only image is good enough. So then what the accelerator is doing is, we break nuclear. Okay, I think you studied about nuclear structure in high school. Nuclear has, like I say, the proton and neutron. Then we accelerate the proton. Proton is also heavy. Proton is just like this size, okay? The nuclear has this size. So then if we use the carbon 13, carbon 12, only 12 the protons are there inside nuclear. Then if you hit the one proton, this nuclear can be easily broken. So we accelerate the proton to the nearly similar to light speed and inject to the material nuclear. The nuclear is broken, the muon comes out from there. Okay, once again. So start to accelerate, inject to nuclear, the nuclear was broken, is broken, and muon comes out. So this is how to take the muon out from nuclear. So that means we are breaking a nuclear. So like a nuclear power plant. So then due to this reason, the accelerator is the length to be just like a nuclear power plant. Okay, very dangerous. So at this moment, we have the target of the carbon, thick carbon, to be broken by the accelerated proton. Once again, accelerate and inject the nuclear, then break the nuclear and take out the muon. So that if you have this carbon target by our hand, and maybe 1 hour later, we can be dead because the breaking a nuclear causes a high radiation condition. So this is a facility just like radiation facility. But of course, radiation safety is quite well. So any people can come in to enjoy the muon science. So due to this reason, we need the accelerator. The accelerator is not cheap, okay? We need a huge amount of cost and money to maintain, to build up the accelerator. So then there are only 4 facilities in the world where we can use muons. One is Rutherford Appleton Laboratory, which is our basement. So the neighbor, the PSI, Paul Scherrer Institute in Switzerland, near Zurich. So, and also the recent one, the J Park, near Tokyo, just beside Tokyo. But this is now a recent one. Another one, Triumph, in Vancouver, Canada. Luckily, I had opportunity to use all of them, and I know the machine quality and beam conditions of all facilities. So what I'm already doing is we have to go to the UK to carry out the collaboration studies with my collaborators, and then sometimes I go to PSI if I can have a beam time in a PSI and enjoy the muon science, and also sometimes I go to JPAC. So unfortunately at this moment, the Switzerland, UK, and Canada are all closed for the foreigners. Then the last 1 year, I couldn't visit anywhere at this moment. So then I'm waiting for the triumph to be open for the world. Canada should open the border. Then I can apply the beam time schedule to triumph and enjoy the triumph beam. This is also a good facility. And long time ago, I went to there and enjoy the nature and the foods and atmosphere and science in triumph. And Vancouver City is also good. So then we can enjoy the science and sightseeing and foods. And also Switzerland is also good. But when I took my students to PSI, some students cannot eat some things because due to the Islam rule. But they can enjoy the cheese and many things. And sometimes they went climb up mountain and enjoy sightseeing and come back. Very nice. So not only for science, but also we can enjoy the world. So, and also there are two characters. We say DC muon source and pulse muon source. So DC means they are continuous, pulse means pulse. So PSI triumph, the DC muon source, the pulse muon are for the JPEG and Raspberry. Then sometimes we have to choose one of each to be applied to our samples. Sometimes we have to choose the pulse, sometimes we have to choose a DC. Depends on the sample condition. So then that is why we have to apply and we have to use all the facility. So then I can skip the detail. So then nowadays, there are two facilities are coming up in Asian countries. One is in China, near Hong Kong, CSNS. This is actually now working, but the beam strength is not so high, very weak. So I've been to here a couple of times and saw the facility conditions. So I'm still working with some people in this facility, and hopefully I can visit again and to start to think about how to use this Chinese facility. But this facility is very, how can I say, in the Midland area, not so easy to access. We have to fly to near airport, but those are far away from this facility, like more than 70 or 100 kilometers. Not so easy to move around in China. Instead, Korea is now building up one more facility, which is a Laon. So this is near Seoul. Then like 30 minutes by a bullet train from Seoul, in Daejeon. So this is a little bit delayed, but hopefully, and also due to the Korean economic situation, the Korean government situation, this Laon project is always being delayed and delayed. But we hope the Laon is coming up very soon. If so, this is not for my age, but also for your age. Maybe all of you can enjoy all the facilities in the world, including Laon and the CSNS. So then you can have more opportunities to enjoy muon science. Okay, we say muon, but just only simple muon is easy to say. But in detail, muon has many characters. For instance, muon has two characters, as I said. It's a plus charged, minus charged. We say the positive muon and negative muon. Of course, each has each character that is different each other. Then we have to choose which one is which for your science. The next one is both of them, the charge, plus charge, negative charge, both are available in the cosmic muon, and sometimes with the cloud muon. These are also different characters. But a cosmic muon, we can have both plus and negative. Then for the plus, we can have surface muon, decay muon. These are also have different characters. We have to choose which one which. And also negative muon, they have decay muon. They don't have a surface muon. They have decay muon. Then how we can use it? For instance, surface muon, we use the surface muon for MUSR and also other like chip experiment. Chip experiment means just like how the control motherboard, PC has a motherboard, how the motherboard shows the malfunctions by using the cosmic ray. This means if we send the satellite to the space, satellites has motherboards and PCs, but a PC sometimes shows the malfunctions by hitting the cosmic particle. So then we can simulate such a situation by using Muon on the Earth. So such things we can do. And also high pressure mirrors and blah, blah, blah. The decay muons are also available for other, the high technology, high technique, the mirror advanced mirror the conditions. And so negative muon, this also has a interesting character. And sometimes we can investigate the shape of nuclear shape, okay, how the nuclear shows the spherical or deformed shape or not. By using a negative muon, we can do such investigation. But this is not in my field. This is a nuclear science field. And also elemental analysis. This is now very fashionable. For instance, if you have a very important, the old goods, like a sword or something, like 1,000 years ago, we cannot destroy that one to investigate the inside of the sword. But by using muon, we can analyze what sort of components are included in such a very important items. Then this is very passionate about this moment in the Rutherford in the UK. So lots of the researchers, like who are working with the museums, they come into Rutherford bringing a very famous, the items. But sometimes the restrictions to bring out such a very important items from museum is very hard. So then we used to have a plan to do such things. There was a very important, very famous, the gold coin, Greek coin, the store in the British Museum. So then in order to bring out such a very important coins, the two British Museum people have to be just beside the coin for 24 hours. That was a strong condition, not to be stolen. Then what's happened in the end is the British Museum suggested to send 2 or 3 people from the British Museum and stay just beside the coin during all the time, during the experiment all the time. Then Rutherford gave up such a very strong restrictions. But still, the Rutherford, our teams, are now trying to find such the opportunity to enjoy. Anyway, what I want to say is the muons are available for any in the very wide range of the scientific field, and can enjoy so many types of science. Not only for MSR, but also for other science you can choose, but all are muon science. So then what I'm going to talk about the use of the surface muon, especially from now on, because if you talk about everything, I need more than 1 week. Then I choose only surface muon to discuss and to explain how we can use the muons to all of you. Okay, please remember, my talk is on the basis of the use of the surface muon. So they come back to regional dashboard, the regional muon facility. So our facility is in here. Okay. Issy sensei, Professor Issy.
Yes.
Can I have a 5 minutes break?
Yes, of course. It's already 1 hour. So you
I don't like personally 2 hours talk, so then the better.
Yeah. Okay. You can take your time for 5 or 10 minutes.
I want to go to the toilet.
Yes, please.
Thank you. Terima kasih.
Okay.
5 minutes we start, so please have a rest.
Okay. We will break for 5 minutes. If you or yes. Okay, no problem. Yes, please. Yes. Okay, for the student, if you have a question, you can write your question in the chat box. Okay, don't forget to fill out the absence, the daftar hadir ya, sudah ada di chat room, mangga diisi. Oke. Oke, kita istirahat sebentar. Jadi kuliah kristalografi kita minggu ini diisi oleh Pak Watanabe ya. Minggu depan kita kuliah sedikit tentang point group ya, point group lanjutkan, kemudian 2 minggu lagi seharusnya kuliah Pak Watanabe kita adakan berturut-turut, namun karena beliau mendapatkan jadwal yang sangat ketat mendadak, sebenarnya sudah deal ya 1 bulan lalu, tapi kemudian mendapat jadwal yang sangat mendadak, terutama untuk ada beberapa deadline yang tidak bisa ditinggalkan pada pada minggu depan ya, tanggal 1 April. Jadi seharusnya perkuliahan 25 sampai 1 April. Jadi beliau minta untuk postpone 1 week gitu. Jadi tanggal 8 April itu baru masuk ke perkuliahan kedua ya. Perkuliahan kedua nanti temanya adalah tentang DFT. Tadi kemarin itu sebenarnya diskusinya DFT dan superconductivity ya, superconductivity. Seperti itu. Nanti mungkin pertemuan kedua akan kita update lagi, baik itu tema ataupun ininya ya, linknya itu seperti itu. Kemudian setelah itu minggu berikutnya saya sudah invite Dr. Michael Manawan. Beliau adalah praktisi expert untuk XRD analisis ya, XRD analisis. Beliau adalah salah seorang konsultan di beberapa supplier peralatan khususnya X-ray ya, seperti untuk X-ray broker itu beliau biasa menyampaikan pelatihan ataupun kuliah-kuliah tentang pemanfaatan X-ray, beserta dengan analisisnya. Jadi kita mungkin sekitar 3 minggu lagi akan mengundang beliau untuk menyampaikan perkuliahannya khusus untuk kita mahasiswa S2 ya, mahasiswa S2. Tapi nanti seperti biasa akan open untuk teman-teman mungkin di prodi lain, di fakultas lain yang membutuhkan informasi tentang XRD. Mungkin ada beberapa mahasiswa yang sudah pernah memakai XRD, terutama mahasiswa S2, S3 mungkin memakai XRD, kemudian masih bingung analisisnya seperti apa gitu ya, analisis serta teorinya seperti apa. Nah itu kita akan undang khusus expertnya. Jadi nanti perkuliahannya memang benar-benar dari expert untuk analisis XRD misalnya, seperti itu ya. Karena perkuliahan kita memang adalah kristalografi dan difraksi ya, karakterisasi itu untuk mengeksplor sifat-sifat material seperti itu. Nah itu nanti mudah-mudahan bisa kita laksanakan di bulan April nanti setelah perkuliahan ini. Itu seperti itu. Okay.
Thank you for waiting.
Yes, okay, no problem.
By the way, are there any questions until now?
Silakan jika ada pertanyaan.
If you can please translate. If you have no question, that means you completely understood or you completely don't understand.
I think it's from until this point they completely understood.
Oh, wonderful.
Yeah, it's wonderful.
Very good, good.
Yeah. Okay.
Okay, can I just start
Please.
again?
Yes, please.
Okay, so they come back to Rutherford Appleton Laboratory. Sorry for waiting. So here, red circle is a, we can come into this red circle area to see the air facility. So here, the Rutherford Appleton Laboratory, this is the oldest building of Rutherford Appleton Laboratory. And we say the target station 1, target station 2. So this one is newer than here. This one is very old, like 40 years old. Then accelerator here. And sometimes, every time in the morning, we have to walk here to access to the experimental area. So walking through here, come into the accelerator area, then they come into this building. So in the morning, all the time we pass through here, especially in the very early morning, like 7 o'clock, 6 o'clock, we can see many rabbits jumping around here. Then the rabbit is very famous in the UK with a Peter rabbit. So then there are many rabbits, but we cannot catch up anything. So in the last 30 years, I tried to catch up something, but not yet succeeded. So the inside transparent view is like that. So the linear accelerator, fast accelerator, and main accelerator with a main link, and come into the target station 1, and this one target station 2. This is for soft matters, just like organics, by using neutron. This one is any materials by using muons and neutrons. So here is a rectangular muon facility. So then come back to the our current photograph. So we have 4 experimental area. The port 2, we say, port 4, port 1, port 3 here. The port 3 is being closed now because we have no budget, no plan to use this one. This one is a general purpose use. So this one is now the being used for like a nuclear physics to measure the radiation, to measure the radius of the proton itself. So these port 4, port 2 are for MUSR. So then I'm talking about these two now. Then what we are doing is 2 types of the researches. One is a muon spin relaxation, MUSR, it's an experimental method. The another one is a computation method, density functional theory calculation, with a DFT. So then they both are completely different. One is experiment, one is computation. So then I've got some students who worked on both, like an experimental student and a computation student. So then this time I talk about the experimental part, muon spin relaxation. So next time I'm not being asked by Professor Lisdy to talk about the DFT, but I'm the experimentalist, not the computational people. Then I try to talk about the DFT calculations, but maybe if you are interested in, please join to us to carry out such a computational, the material science. Such kind of people are also very welcome. I'm now recruiting such kind of the students who are interested in the computational method. That means they are sitting in front of the PC and calculating all the time by using a supercomputing system of Riken. So the image on the mirror side is just like that. So then they import for recent physics, what the important point is how to understand the magnetic interactions between the magnetic spins. Okay, so the magnetic spin interaction can cause the fluctuation properties of the magnetic spins. So how easy, how fast, how slower, and how static those spins are behaving. That is the main part of the material science. Then we put the muon in near the magnetic spin. The other doctrine, muon has a spin of half. Then this muon spin can also have the magnetic interaction between magnetic spin. Then if we observe this muon spin, we can understand indirectly the property of the magnetic spins. So this is an interesting property of BSR. But important point is how we can understand such a magnetic interaction between muon spin and magnetic spin, and how easily we can have the information or the magnetic spin, the dynamics. So then the another other characters, how can I say, what is the advantage on MUSR compared to the other techniques? Do you remember I talked about the MUSR to be just like NMR? But of course, MUSR is completely different from NMR because due to these characters. What sort of the characters important for for material science are like that. With the gamma, it's we say the gyromagnetic ratio. That means if you apply one fixed magnetic field, how quickly muon spin is precessing around the magnetic field. That is a Lama spin precession. Maybe some of you already studied the Lama spin precession motion. Lama spin precession motion. So that is the, how can I say, special character for the magnetic spins in the magnetic field. So then if we apply the same magnetic field, how quickly the spins are rotating, that is called, that related to the sensitivity as a magnetic probe. So the proton has a quite high, the gamma value, the gyromagnetic ratio, but muon has the highest gyromagnetic ratio among magnetic probes. That is gamma value is 135.5 megahertz per kilohertz. That means if you apply 1 kilohertz, 10, this is 10, 1 kilo aerostat, the muon is precesses the near with the frequency of more than 100 megahertz around the magnetic field. So then if you apply the muons, maybe we can have much more high sensitivity compared to the proton, that means compared to the NMR. So the most important character is the sensitivity and also how the sensitivity is. So, okay, this is just like an image, okay? So nuclear dipole with an electron dipole. But nuclear dipole is different from electron dipole. Electron has a spin. Nuclear also has a spin. But nuclear dipole spin is much, much smaller than the electron spin. Usually, nuclear dipole field magnetic spin is 2 orders smaller than electric spin. But this is magnetic dipole. Magnetic dipole is just like a magnet, okay? Magnet can cause the magnetic field around the magnet. This is very just a basic knowledge for elementary school, okay? So in the material, those kind of nuclear dipole can cause around 1 Gauss around the muon inside the material. So how large is 1 Gauss? That is the question. On the Earth, okay, as you know, the Earth has a magnetic field. So then we say Earth field. The Earth field is just around 400 milligauss on the Earth. Even in Indonesia, the magnetic field from the Earth is just like a half of the 1 Gauss, half Gauss. But inside the material, nuclear dipole field can make just like a 1 Gauss. But 1 Gauss is quite a good enough field for muon to detect. So such sensitivity is quite variable for the material science. We can see the small amount of the magnetic moment inside the material. And this one is the most important character of the MUSR. The muon has a self-spin polarization. Self-spin polarization means from the beginning of the creation of muon, all the muons, surface muon, has the same spin direction automatically, even in the zero field condition. The nuclear magnetic resonance, what they are doing is we apply the strong magnetic field to make this kind of spin polarization of the nuclear dipole. However, even we don't apply any magnetic field to muons, muon can show the self-spin polarization. That means the MUSR can do any resonance experiment in the zero field condition. Zero field condition means quite the ideal conditions for research in the magnetic materials. So that we can say the muon can give us the ideal data they are taken in the magnetic materials. Okay, if you say magnetic materials, there are many kinds of magnetic materials. For instance, porosity is now studying the high TC superconducting oxide. But if you say superconducting oxide, that seems to be like a metal. But basically, the superconducting oxide high TC superconducting oxide is the insulator and also the magnetic material. That means that we have to understand what sort of magnetic interactions are there in the material. So then MUSR is a quite ideal the tool to study such kind of magnetic interaction. So okay, this is the image of the MUSR, what we are doing at Rutherford and Triumph and everywhere. All the same, basically the same, principle is the same. So that we throw in the muon into the material, okay? We throw in the muon into the material by using the accelerator, okay? Say this one accelerator, make a muon and throw into the material. So material is just like a sample, we say target sample. Then we allocate forward and backward counter. Counter means how to detect the muons. Then the muon is inside the sample, but counters are outside the sample. So that we cannot directly see the muon, of course. So then how we can detect the muon signal is, luckily muon can give us a signal from the muon. That signal is coming out from the sample and hits the counter. Then we can have the signal from the counter, then we can understand the muons, the behavior. Okay, this is due to the lifetime of the muon. Lifetime means muon decays to other particles. The muon decays the other particle. In our case, this means positron. Positron means electron with a positive charge. Okay, so the one muon emits the one positron and detected by the counters, forward counter, backward counters. So then what we do is just counting the number of these positrons. Okay, just only count, simply count 1, 2, 3, 4, 5. That's only. Then they just forward counters, backward counters, how many the events we counted by forward and backward counters. Then following this equation, we see the data. Data means we say asymmetry parameter. Asymmetry parameter means how much muon spins are gathered, just means in the same direction. Okay, please remember this. Muon spins are aligned in the same direction. So then if the asymmetry is complete 100%, all the muons show the same direction. If we say 50% asymmetry means 50% of muons doesn't show this spin polarization in the same direction. Then we calculate this asymmetry. Then we have this kind of figures in the paper after we calculated the asymmetry parameter from the raw data. So then if you see the MUSR paper, you can see this kind of the strange figures. But how do we understand this figure? That is the next question. For instance, red one, just gradually going down. Why? That is gradually going down. Then how we can understand what sort of information from this figure? And also black one, blue one, show the sort of the wigglings. Then go down, go up, go down, go up, go down, and go down, go up, blah, 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 just like a snake. Okay. So what the meanings of this up and down wigglings? What sort of meanings we can understand from the wigglings? That is the key question: how to understand the MUSR study. As long as you understand this property, not so difficult for all of you to read MUSR paper. Then I talk about the principle, how to understand this from now. Okay, so then as I said to you, muon has a lifetime of 2.2 microseconds. Then what's happened is muon decays to the positron and 2 neutrinos. Then we detect this positron by the forward backward counters. Then sometimes we say counters are to be the muon counters, but exactly saying this not a muon counter, is a positron counter. So that is a nuclear science technique. The interesting, this positron is being emitted mainly along the muon spin direction. Okay, there are many positrons are coming out from the muon spin direction, but less against the muon spin direction. On the other hand, neutrino is completely the opposite side of the positron. So neutrino, I talk about the complete difference. Neutrino is very important nowadays for the particle physics. How much mass the neutrino has. So if neutrino has 0 mass, we don't need to change the principles of physics. But if a neutrino has a mass, then we have to change the basic knowledge of physics. So now to measure neutron mass is now very fashionable research area for the particle physics. So JPAC, the Japanese scientists, worldwide scientists are now studying how much neutron mass are there by using the accelerator. So maybe if we can decide the neutron mass, that could be like a worthwhile to have a Nobel Prize. Okay, so then from now on, I talk about the muon data, but please understand that data is gathered by the positron. Okay, positron. So then come back to the realistic condition. This is a real spectrometer for MUSR. So please see this one, black one here. These are positron counters. The sample is around sitting in the center of the spectrometer, and then counted the muon emits the positron from the sample, and the positrons are counted by these muon counters. We say positron counters. This is just a plastic counter, the doped by lead. Just very simple. So these are my old students, Dr. Letono and Dr. Fahmy. They are now working in ETS as lecturers. So they studied MUSR for 3 years with me during the PhD courses. Then after the graduation, they've got a job in ETS. Then now they are now studying the material sciences. But sometimes we talk about the MUSR. Okay, the cost is very big. I calculated this one, translated this cost to be in rupiah. So just one spectrometer in total cost is 13 billion rupiahs. So very expensive. So if we break this one, we cannot build up this one anymore again. It's too expensive. So then what we have to use this kind of the very expensive machines at the Rutherford. So but as long as we use exactly, we don't break, we can have very advanced data to discuss the advanced physics. So if you join to us, of course, you can enjoy to use this kind of very expensive, but very funny and very interesting equipment with us. Not so difficult. Just only they started to learn about the MUSR just after they joined to me, but they can operate this kind of the spectrometer very easy. Okay, so the MUSR spectrometer. So how do we count the positron? I demonstrate from now, okay? So these are forward counter. This one is backward counters. Each counters are constructed by the sum of the positron counters. They segmented like that. This is just an image. We have many segmentations on each counter. So here is a sample, okay? This is a basic idea for the MUSR spectrometer. So for any facilities in Canada, Japan, PSI, Switzerland, and Asian countries, the concept of MUSR spectrometer is all the same, everything is the same. Put the sample in between the backward forward counter and count the positrons which are coming from the sample, which are coming from the muon. Then we inject muon inside the sample, okay, like that. Then the image is not so good, muon passing through the sample, but please image the muons are stopping inside the sample. Then after stopping inside the sample, muon decays to the positron with a lifetime of 2.2 microseconds. Okay, so that positron can have a good enough speed to come out from the sample and hit the counter. Image like that. The muon coming in like this. This is beamline direction. So the muon spin direction is like this. They come in and emit the positron, and the positron hits the counter. So the image is like that. So then when the positron, okay, once again, when the positron hits the counter, what's happening is counter creates sort of the light, but very small light. We cannot see by eye. Okay, spin there. They put in a light here, light here, right here. So because the positron counter is doped by red. So when the charged particle is passing through such kind of plastic counter can create some sort of light. How much light we can see is, usually we say like 30 photons per one positron can be created in the counter. The 30 photons, the very small. For instance, the light is on the basis of the photons. Okay, the photon is a quite small number. Usually we have much more photons as a wave, then we can understand the light itself. So then very tiny the light cannot be detected directly. So then how do we use is we amplify. Okay, we amplify the signals. That means amplitude of the signals is very important. How to amplify the signals is the high technology given from the nuclear science. Then we put the photomultipliers like this on a counter, then detect the muon signal. Then this photomultipliers is very small like that. We are now using this kind of photomultipliers. Okay, so very small one, but very expensive. For instance, 40 million rupees per each. Then how many photomultipliers we are using for the spectrometer is nearly 200. So we are using 200 photomultipliers to amplify the positron signal. Then how much the photomultiplier can amplify is more than 10,000 times or 100,000 times the bigger signal. That means like a 10 to 3 to 10 to 4 times bigger signals we can see. Then we can have the very small amount, the positron signal to be as the real electric signal. Okay, the 4 Becquerel counter here. Then we can count number of the positrons. Then the positron hits a counter. Then photomultiplier can give us the electric signal like that. Then we can gather this electric signal by using some detectors. Then we can count up how many the positrons can pass through these counters. Then we can understand the MUSR signal. Okay, just only counting a number 1, 2, 3, 4, 5, just only, but up to millions the events we count up. Then this is a realistic data, which is obtained by MUSR. So please see this one the time. This one the time. That means that 0 time means muon arrives at the sample. Then start to increase a signal here. Then muon event, that means the number of the counted positrons. Then time here, the counted positron is decreasing like that. Then this one is a muon lifetime of the 2.2 microsecond. So this is the low data. Okay, this is the low data. But the realistic published paper is completely different from this. Completely different. Then why we can have such a completely different data from this low data? This is just like mathematics. Right? Please understand the muon lifetime. Lifetime means just a decreasing number of muons which can be available. So for instance, these muons can survive up to like a 20 microsecond. So a long time, the survival. It's very same with the human beings. The human being's lifetime in Japan is now nearly in between like 85 years. So then within 85 years, the number of the people are decreasing year by year. The same, lifetime is like that. So if we have logarithm scale plotting like that, the lifetime becomes the straight line and disappear completely. Just like up to 20 microseconds, we can have the signal like this. Then we gather the number of the events by using a PC, okay? The photomultipliers, these are photomultipliers. Then gather the signal and send to PC and count the numbers. So this one, they forward the counters, counted by the number of events. And then this lifetime. The lifetime, can decrease the number of the muon events at time t. Okay, so this one you forget about at this moment. So how this one is GZ. GZ means how the muon spin polarization is changing in time. We say relaxation property. the relaxation function. So the forward and backward. Why here is negative is the forward, backward, the position is completely opposite to the sample. Okay, time zero. The time zero means this value. This value is a time zero number of the events. The lifetime here. Lifetime means this one. Time by time, number of muons, they will be decreasing. Then remember GZ. It's a muon spin polarization, depolarization function. That means how much muon spins can keep the polarization in time. Then the forward backward counters. Then what we do is we just simply calculate the symmetry parameter like that, forward minus backward, divided forward plus backward. So that means how much muon is now the polarizing in the same direction. Okay. So then this one is a little bit complicated function, but if we calculate the symmetry parameter, so this part, lifetime part, disappears. Okay, lifetime part disappears, and then the only GZ is left. And A0 means the asymmetry parameter at time zero. Time zero means how much the muons are polarized to the same direction. Then we say the A0, that means like just only simple parameter plus ZZ. Then we can describe the asymmetry parameter by using only the relaxation function, which is the depolarization function. That means in time, how the muon spin is changing, the muon spin polarization is changing in time. That is important. Then we can concentrate on the relaxation function only. Then as long as we discuss the relaxation function, we can understand the motion of muons. So how? That is the next step. And in materials, just only by image I show you now. Okay? The forward, backward counter there. Then the sample is here. The muon stopped in the sample with keeping this muon spin direction just after muon stops in the sample. Then start to decay with a lifetime of 2.2 microseconds. Okay? Then positrons are emitted from the muon and hit the counters, both counters. So then as I talked to you, the positron emission is much bigger the following this muon spin direction. So in this case, what's happened is we count the more positrons by forward counters rather than backward counters. Okay? If so, let's calculate the symmetry parameter in this case. The number of the forward is much bigger than the backward. If so, the asymmetry parameter is forward minus backward divided forward was forward plus backward. That means the forward is larger than the backward, the asymmetry parameter becomes positive, okay, bigger than zero. If the muon sees to the our direction, okay, that means the muon spin polarization is in parallel with the counters. What's happened is both counters, they counted the positrons in the same ratio. This side is many, but backside, this side is less because the muon spin direction is in this direction, polarization in this direction. So around here, the counters, the spectrometer counts the many positrons by around this area, okay? If so, what's happening is the number of total counted number, of the by forward backward counters are similar. The forward backward same. Then asymmetry is forward negative backward minus backward divided by forward plus backward. Okay, so forward and backward show the same number. The asymmetry becomes zero. Okay, I change the spin direction again. Okay, if the muon spin directs the backwards the counter direction, the condition is completely different. So now the backward becomes bigger. Number of the positions they counted by backward becomes bigger. Then asymmetry parameter becomes less than zero. That means negative. Okay, let's say the muon spin directs this direction. So then around this area, the area of the counters counted the positron with is equal the number. Then asymmetry becomes zero. Okay. They come back to the first one. Okay, muon spin directs the forward counters. Forward counters counted the more muons. The asymmetry the positive. So then if they are in parallel to the counters, asymmetry becomes 0. And muon polarization directs to the backward counters, the asymmetry becomes negative. And this condition, asymmetry again becomes 0. So in total, if the muon spin, okay, if the muon spin stops inside the material, then if the muon spin shows like a precession motion like that, okay, precession motion, just like rotating inside the sample, how we can see the asymmetry parameter, okay? Asymmetry parameter is the most important parameter for MSR. Then becomes like this. So then what happens in the end is we can see it's just like a oscillating property in the asymmetry in time. Okay, you understand? Once again. Okay, once again. So if the muon spin is rotating inside the sample, we can see in the end the oscillation property of the asymmetry parameter in time, like this. Okay? So then the muon spin is smoothly rotating inside the sample. This oscillation property becomes cosine-like. From 1 to 0, 0 to -1, -1 to 0, 0 to +1, +1 to 0, then this becomes cosine curve-like. So then there are more images like that. So if the muon in a realistic image is like that, if the muon is interacting with electric spins, and if the muon start to rotate in phase like that, all the muons show the same rotating property. That is the same condition with that I spoken to you. Okay. So this case, what's happened is asymmetry parameter against the time becomes like this. Okay, asymmetry parameter shows like a cosine oscillation following the oscillation of the muon inside the sample. Then we inject, after we inject the muon into the material, if the muon shows like an in phase, the coherent, the precession motion inside the material, what we can observe in the end on the PC, okay, in the PC is we see such like kind of the cosine curve property. Then when we observe this cosine, the oscillation property in the end, what we can declare is all the muons inside the material shows like a precession motion in phase, the same precession motion in phase. So how we can understand this kind of muon precession motion is all the muon inside the material, they can feel the same local field condition. That means at any muon positions, the muon can see the same, local field inside the material. So then this corresponds to the appearance of a long-range order state, just like a magnet. So in order to discuss this kind of situation, just only experiment is fine, experiment result is also fine, but sometimes we need a much more detailed investigation by using computational technique. So even though we observe this kind of cosine precession, we can declare the appearance of just like a magnet state. But in the end, if we discuss more deeper points like a muon position, the hyperfine field, and multi properties, we need a computational task, computation jobs, which is completely separated from different from the experimental technique. That is the computational sense, DFT. Maybe next time I talk about the DFT, the studies how we can carry out by using what sort of the machine conditions. Okay, but usually this like a beautiful cosine precession is not so easy to be observed because real materials are not so clean all the time. Sometimes dirty, sometimes they have many defects inside samples. So then they please understand this is a very ideal condition for magnetic materials. On the basis of my experiences, maybe less than 10% or like a 20%, the possibility we can see this kind of the cosine precession motion, but almost of the magnetic materials shows a different property. So then I show there's some properties, but please understand, please be aware. So this one, I'm not talking about a very ideal condition. So then in one extreme case, then I next talk about the different conditions, but all conditions can cover all of the data property. So that means as long as you understand some sort of these image-like conditions, you can understand all the MUSR data. Anyway, as long as we see the cosine property, we can understand the motion of the mu inside the inside the material. Then how to analyze this, the frequency and those others, we apply the relaxation function. So then now relaxation function becomes very important to understand in the physics. Then we can apply, for instance, in this case, cosine curve. So this is a realistic case. Okay, please see. If the mu spin precession is in the same direction but different frequencies, so we can see the damping property of the mu spin, the precession motion. This is a very realistic condition because in the real materials, we cannot guarantee the complete same local field condition around the muon. Some muons, they rotate very slowly. Some muons rotate very quickly. Then we can see the damping property. The damping property means just like a distribution of the rotating the frequency. Then from this, the parameter again, we apply the relaxation functions. Then they will analyze this data. So then, as you can see, this one is I wrote down the like a mathematical method. So it seems to be very beautiful, but the realistic data is not so like beautiful. Then how to apply, how to choose the analysis function is a key point, key technique for MUSR. This is not so easy. Then but as long as we discuss with the senior guys like me, we can suggest appropriate analysis functions. But there are not so many analysis functions in the world at this moment. Then if you remember some sort of kind of the like less than 5 types of analysis functions, you can use MUSR. So this is still, we can see a case, we can see the mu spin precession motion. But in the extreme case, we can apply the analysis function like that. So some parameter is corresponding to the NMR parameter, but I want to escape such a detailed condition. Okay, this is the most extreme case. Okay, muon spins, all muon spins show the complete different motion. Rotation direction is different, and speed is also different. In this case, we no longer see the muon spin precession properties in the asymmetry. Then what we can see is just only the decay of the asymmetry parameter. Decay of the asymmetry parameter means the muon spin polarization is being lost in time. Now please see this figure so carefully. In the beginning, at time t, all the muons are aligned in the same direction, but start to depolarize in time. So in this case, we see only the decay of the asymmetry parameter. So in this case, the problem is how to analyze this kind of the extreme time spectrum. That's the next question. So then sometimes we have to think about the very special cases, special functions, but sometimes we simply can apply the very simple functions. For instance, sometimes we use this exponential, we say Lorentzian function to analyze this kind of the property. But this Lorentzian function is very important to discuss the spin dynamics because in order to discuss NMR data, we always use this function. So then this function is a very good function to reproduce the spin dynamics. Then also this is available for MUSR to analyze the data. Then applying this function, sometimes we can discuss much more detailed the conditions of MSR. So I talked about 3 cases now, but only these 3 cases are good enough to discuss the realistic data. So as long as you understand these 3 cases, the next question is how you can apply these cases to realistic data to discuss the result. That's only. So simply speaking, MSR is not so difficult, but for young students, young people who don't know about MSR, the MSR seems to be just like a very heavy tasks because we have to go to the foreign countries and we have to use the accelerator, we have to use the very expensive equipment that causes a very big gap to the young people to use, to think about. And also, as long as we cannot image the muon spin motion like that, not so easy to understand the MSR time spectrum. So that is a very big gap between the young people and MSR. But as long as we understand, like in a schematic viewpoint like this, the MSR is not so difficult, much more easy compared to the neutron, compared to the NMR. So then please understand, even though we use a facility, but the principles, MSR, are very not so difficult. Okay. Then sometimes we analyze this sort of the extreme case by using a Lorentz function. But this one is T1, corresponding to T1. That is the same with the NMR. Okay, so now these are descriptions of the MSR techniques. So as long as you understand these techniques, you can understand what's going on real materials. So then from now on, by using 10 minutes, I show you some examples of MSR, the science, MSR studies as much as possible. Okay, but before that, do you have any questions? If you have questions, I can simply answer to you now because from now I talk about the realistic experimental examples, which is much more complicated and difficult for you to understand.
Okay, if you have any question, please raise your hand or put in the chat box. Okay, I think it's okay. Watanabe-san.
It's okay.
Oh yes. Yeah. Okay.
Hmm?
Okay. Any question? Sorry. Oh, Eka?
Yes.
Oh, yes. Oh, okay. Yes, please, Eka.
I want to confirm that the Muon physics, according to the direction of the field produced by the crystal, so that is affect the asymmetric curves.
Good question. Because exactly speaking, not. Exactly speaking, not. If you talk about the detail, it's not so easy because it depends on the structure of spectrometer. But technically, we can use a powder sample and single crystal sample both together, and asymmetry doesn't change. So we can see a little bit different properties of time spectrum if we use both, like powder, single. But usually we can use powder. That is also another advantage for MSR. For instance, for neutron, in order to discuss a spin structure, we need a large single crystal for neutron experiment. However, we don't need to have such a large single crystal for muon experiment to discuss the spin structure. But on the other hand, we need a DFT calculation to discuss a spin structure, which is, again, a bit complicated. But we have the computing resources with us in RIKEN, and also we are now developing how to approach to this problem. So then I can see the Budi dependent on the name here now. Budi, are you fine?
Yeah, I'm fine, but I cannot show my video.
Why?
Is that okay?
Anyway,
it's kind of a bit mess in here in my house.
I see. I don't want to see. And this Budi Adipurna is my first student from Indonesia and worked on the DFT. So year by year, I have some students, then they are still developing the way to do. So then we have some fixed way at this moment to discuss the spin structure, even using the powder data. Okay? Hi.
Thank you.
Oi. Sama-sama.
Okay. Polycrystal or single crystal is no problem. Yeah, the MSR. Yes, it is advantage point using the MSR. Okay, any other question or comment? Okay, no? Okay. Okay, no other.
So now we have 5 minutes or 10 minutes to go.
Yeah, yes.
So then I show some examples. So then if the time is up, I talk about them in the next time.
Yeah, okay.
Maybe shall I talk about the DFT or superconducting state next time?
Yes, of course. Yes, of course.
Okay, so then I talk both because it's easy for me.
Yeah. Yes.
So next time, I spend the time a little bit more about the other magnetic materials, but to introduce the next talk, I simply talk about the superconductors first. Okay.
Yeah.
So as you know, the superconducting state is very important to be studied, even from now. It was found more than 1 century ago, and discussed by acceleration. Now we partially understand the superconducting property, but still there is still the top physics. Then how do we discuss the superconducting state by MUSR, okay, experimentally? So I show you now how do we study the MUSR by the superconducting state, because the prosodicity is studying the MUSR by the superconducting state by MUSR. So how to discuss this one. So okay, let's say here is a superconductor, outside superconductor. Then if we apply the magnetic field, what's happened? Okay, magnetic field in this direction. Maybe some of you already studied from the prosodicity's lecture. Then this magnetic field is distributed inside the superconductors. Okay. Then field is applied, and outside the material, of course, field is constant. But if the field comes into the inside of the superconductor, what's happened is this magnetic field is decreasing in a distance from the surface. This is the one character of the superconductor. So if you want to study why such a situation happening, please ask the prosodicity. He knows about this. Then we say this is the Gzai means the coherence length, or sometimes penetration depth. Then in order to discuss this important parameter from MUSR, we apply the much more stronger field. In the case of type 2 superconductor, the distribution of the magnetic field inside the sample becomes like this. Type 1, there is no magnetic field inside, but type 2, sometimes we can see the penetration of the magnetic field like that, making the flux state. The magnetic field is distributing like this. So this can be this knowledge is available from prosodicity. Then from inside to the superconductor, we inject some muon, okay? Inject some muon from outside to superconductor. Then what's happening is this one is like a schematic image of this distributing the internal field, like a magnetic field inside the superconductor. So not flat, just like a go down, go up, go down. So if you put the muon inside the superconductor, some muon stops here, some muon stops here, stop here. That means this muon see the different magnetic field compared to this? If so, what's happened in the end? If we think about Raman precession motion, this muon shows a different Raman precession motion frequency compared to this. So this muon sees a slower magnetic field compared to this. This one is larger. That means the Raman spin precession frequency of the muon is much faster than this. So that means I show you already the as a second case for the muon spin precession. Then, interestingly, this muon spin precession motion is related to the disk xi. Xi means like a penetration depth. Then this one, muon spin relaxation rate, is corresponding to the penetration depth. Then that corresponds to the effective mass of the superconducting state. Just I don't talk about the detail of this. What is the M star? This effective mass NS. NS is the density of the superconducting the Cooper pairs. Then this one, then the density of the superconducting electron pairs is a key point to discuss the superconducting state. So then, but interestingly, we can discuss this parameter directly by using MUSR. So this one is much more good schematic view how to understand the MUSR time spectrum in the superconducting state. So in the superconducting state, in the type 2 case, then we can see the sort of distribution of the abricot the lattice. That means the magnetic field is distributing like that with the abricot lattice. So then if we put in a muon inside the this abricot state, that is the question. So this one is the mathematical view of the abricot state. There is a minimum field is here, maximum field is here, and that is distributing, and it can be calculated by using some sort of equation, fixed equation. The average is B. Then if we stop the muon here, the bottom point, muon start to show the very slow rotation. However, if the muon stops at the high field position, muon shows a much more higher, the faster Raman spin precession motion. Then again, slower one, maximum one shows much more higher. Then if we put in the many muons inside superconductor, some muons shows a much more faster frequency, but some muons shows a slower frequency. Then what we can see is this one, a normal state muon spin precession property. Okay, there is a very natural decay here. But in the superconducting state, due to differences in the Raman spin precession motion, we can see the decrease of the polarization property like that, from blue to red. This is realistic data, so there are many parameters, the factors why we see the small kind of the differences, but we can definitely see differences, okay? So this one is how to figure the superconducting state by MUSR. On the other hand, this one is my data, all data. This one also high TC data, normal state. We can see the very nice muon spin precession like that. But in the superconducting state, the muon spin precession motion shows a sort of large, the damping property, just like a muon spin relaxation property appears. And this damping property becomes stronger with decreasing temperature. So this difference is caused by the superconducting state. Then damping rate is becoming higher, and becomes like this. So this temperature dependence is also very important to discuss the superconducting state, because this one, they completely corresponding to the density of the Cooper pair. Okay. So then this one is very old, the data taken by the experimental data on the high TC in the beginning of the high TC history. So this one is corresponding to the superconducting the electron pairs density. This is the coming up to the TC. So this, the temperature dependence of the density of the Cooper pair can be fitted by the theoretical function. Then we can discuss a TC and some sort of Cooper pairing mechanism. But same things can be done by using MUSR, by using this temperature dependence of this relaxation rate. So then once new superconductor appears, what the researchers do is we simply measure the temperature dependence of this muon spin relaxation rate. Then we discuss the pairing mechanism of superconducting property. This one is also same. Then if we discuss the Cooper pairing symmetry, there are some the models or types to distinguish which the model is the appropriate to discuss the data. This one is also the data to be done on the high-TC samples. So this one is very old data. Then we can discuss the principal property of the superconducting state, even using MUSR. And now in the physics field, MUSR is recognized to be a good experimental tool to discuss the superconducting property. So then if you're interested in we can show much more detailed things, and we can show the detailed path how to access to this data. That is important. Okay, so now the time is up. So I have more example like that, blah, 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 blah. So I will talk about these in the beginning of the next talk. Then they come into the DFTs and some sort of the explanation of the high-TC, the property. Okay, this is good.
Okay, thank you very much, Watanabe-san, with a very nice talk, already 2 hours actually,
right.
But I think it's a very fast because the topic is quite very interesting.
Sorry.
For me also, it's very interesting because there are some new information, something like USR for volcano. You can use the MUSR for volcano and also for to find the secret room in a pyramid. Okay, it's a very interesting a lecture. Okay. Any question or comment or suggestion or anything? Okay. I think some of students should be okay. One message. Okay, now. Okay, Pak Togar. Yeah, also Lucy Sang also here. Ai Sang, Saragi Sang also here. Budi also here. Okay, any question? Abdan, you have a question or Yati? Oh, okay, Abdan.
Yes, I have a question.
Yes, okay. Okay.
Thank you for the nice talk, Professor Watanabe. I have 2 questions. The first one is, in the beginning of the presentation, you mentioned about DC Muon source and pulse Muon source. What the difference between these two? And the second question is whether the 2 source Muons have the same case on the asymmetry curve that you mentioned. There is the 3 case on the Muon spectroscopy data.
So second question, please again.
Second question is whether the 2 source, pulse Muon source and DC Muon source, has the same case in the asymmetric curve.
Yes. So second question first. It's yes, completely the same. It doesn't change so much. So then I have can you see here?
Yes.
Yes.
Can you see? So just what's the difference DC and pulse? Simply beam structure. It depends on the accelerator structure. So okay, we see the time t here. Okay, time t. Can you see? So
yes.
if we detect muons, how we can see the DC muon is just like a part, just 1 muon, 1 muon, 1 muon, 1 muon, 1 muon in time. Then this time difference is around 4 to 8 microseconds. This is DC beam structure.
Okay.
So then if we detect only one muon, then one muon can give us a signal in between this time. The one muon can identify only one positron. That means that within this short time, like 8 microseconds, we can increase the resolution of the detector as much as possible. That means a higher resolution. This is DC, PSI, and Triumph. Okay, both are in the nice places, okay, Vancouver and Zurich. Wonderful, super wonderful, very expensive. Super expensive, but very wonderful. On the other hand, pulse muon, okay, time here. This is Rutherford and JPAC. Pulse muon, just like a pulse. The many muons, like 1,000 muons are in the pulse. Okay? Then pulse structure, next pulse is 20 milliseconds. Millisecond means all of the muon in this pulse completely disappears before the next pulse comes in. So that means that we can measure the long time as much as possible in between here. However, we cannot identify which muon is which. That means resolution is not so good, but we can measure in time, long time. That's the difference. So basically, how we can say is pulse muon is good for small spins. DC muon is good for magnet, strong magnet. That is why I said we have to choose facilities. Which one is better for us? That's the difference. However, just after muon stopped inside the sample at T0, time 0, all conditions are same. Muon spin is just muon spin. Then asymmetry doesn't change. Just only resolution problem and how long we measure the data. That is only the difference. Very simple. Okay.
Okay.
Okay. So this is a difference between pulse and DC, continuous muon beam. No different. There is no difference in the data acquisition and asymmetry. Yes. Okay. What? Any question? Okay. Watanabe-san. This also. Yes. Just a simple question. If we have a thin film, for example, a thin film, because you said that the beam or the both pulse and DC can measure the single crystal or polycrystal. How about the thin film? It is possible to measure a thin film?
Okay, of course, possible, but only one place, PSI.
Okay.
They have a very special facility for thin film.
Okay.
The compression is very strong, but it's like a complete #1 beam, dream beam for thin film.
Okay.
And for instance, the thin film YBCO was measured in the past. Just mean the checking, that means the thin film means we can control the muon depth from the surface. So that means the PSI, we can measure up to around 100 nanometers thickness by changing a depth. But 200 nanometer is too thick already. But 100 nanometer thin film can be measured at PSI. Possible.
Oh, possible. Okay. So what is the main parameter for measuring the thin film? Because you know, in all recently a lot of devices for the application, they always make in the thin film. So it is possible one time that we can measure also in Rick and Rao muon facility, or you don't have any
thin film is not good for us.
I see.
Completely impossible. Only PSI. They have ultra slow muon beam, but others don't have. Just only PSI. So the experimental conditions, not so difficult. Of course, the physics theme is important. Of course, physics is important. The size has to be 20 centimeter, 20 millimeter by 20 millimeter at least. This size, so the same film we need, and high quality and this size, and also stable in the air. Unstable sample is not so good. Stable in the air and this size of the sample is available. These are minimum conditions.
Okay. Okay. Any other question or comment? Please raise your hand. And another thing that we already also measure, especially Lucy Sang and I Sang here, measure the sample for the solar cell sample. You kindly help us to set up the light source. Can you briefly explain about the advantage of your setup to put the light source in the system, MISA system?
Light source, that means we can have the synchronization between the muon and the light source, especially pulse source. Even though we apply the light so strongly, the sample temperature doesn't change so much due to the duty cycle. So that is advantage.
Okay.
And also we can measure the long time property. That is also the advantage.
Okay.
But unfortunately, strangely, light experiment cannot be done at PSI, and not so easy for Rutherford. But of course we can do, but they don't like so much.
Oh, really?
Because they due to the difficult how can I say, the preparations. So they don't like. So and JPAC now impossible. Triumph is impossible also, of course. Interestingly, our facility doesn't mind to use.
Okay.
That means that as long as I work, no problem.
Okay. So in this just outside of the science actually. So how about the situation in this pandemic? Is it still running or already stopped?
No. It's due to the our Japanese city government. So then we stopped the national emergency alert the last week because the number of the detection became lower. But now after we stopped everything coming up again. So maybe we will face to the fourth wave from next week. Very bad because the Japanese government cannot control the Japanese citizens. For instance, we have no lockdown like yours.
Okay.
The vaccines are delayed. They cannot buy as scheduled.
I already did the first vaccine.
From
university.
Wonderful.
Our vaccine is what's vaccine? Sinovac vaccine.
Chinese one.
Yes, Sinovac is not a visa. I think in Japan it's visa. Yeah.
Maybe my time will be in the next year. Very slow.
Oh, really?
Very slow. Very slow.
It's quite slow.
For instance, the elder persons above the 65 years, we have more than 35 millions. 35 millions. But Japanese government has got only 4 million. Not 4 million. This 0.4 million vaccines.
Oh, really?
Complete city.
Yes, it need a long time to.
Very bad. Very bad. So, but maybe Japanese government would like to open the border as soon as possible. But the problem is the new types of the virus, like British type.
I see.
That is spreading. That is a problem. So now Japanese government is very hesitating. But
Oh.
for my view, it's very silly.
Oh.
Mm.
Okay. Okay. Another question. Oh, Suchi already here. Is Suchi, do you want to ask a question? Yes.
Yeah. Hello, Watanabe-san.
Nice to meet you again. Are you fine?
Yeah, I'm good. I would like to ask about negative muon. It's about elemental analysis for history thing, for example. So actually, I already hear about this in JPS meeting, but I don't know how to get elemental analysis from USR time spectra. So
No, we don't
could
use
you
this spectrometer.
not USR time spectra? So
No.
how do you?
We use a gamma ray detector.
Oh,
Gamma ray.
gamma detector.
That is completely different. That means that we moved out the spectrometer and put the gamma ray detector around the sample. That is completely different because the negative muon can will emit the gamma ray from the sample with a muon gamma ray. Then we detect the germanium type gamma ray detector, which is very expensive. Ishida-san has some.
And then what kind of data that we will get? I
No,
mean,
just from gamma ray detector to the PC is automatic. It's a completely established. Then we see the energy and some peaks, gamma ray peaks. So as long as we can determine the energy value for each gamma ray peak, we can determine and also height. The height is corresponding to the ratio of the atoms. Then we can investigate the components. What sort of the atoms are there inside the material and how many? So the experiment itself is very easy. Just put the sample, then put the gamma ray detector and wait a couple of days, just only. Then we can discuss. The experiment itself is very simple, but very expensive and complicated. So if you can bring something very historical from Indonesia to Lazaport, they are very willing to give you the beam time, of course. Please steal something from museums.
Okay.
So this is like XRD time spectrum.
Very similar.
I mean,
very similar.
The principle. I see.
Very similar. Not the same. Not the same. Not the same. But very similar.
Okay. Thank you.
Thank you very much. Okay, Budi also raised hand. Okay, Budi.
Yeah.
Yes.
Suddenly, I have a question related to high statistic data. Because I heard from the last Muon meeting that Steve Blundell is already using the very high statistic data. So my question is, how much is the maximum can one sample have of about how many million event can be so the maximum statistic can be approved by the reviewer for the experiment.
Now, of course, it depends on the physics because usually we have 15 to 30 million events per data point. It takes about 1 hour half at PSI, but only like a 20 minutes at Rutherford, 20-30 minutes at Rutherford. So then, if you have 4 days, how many data points you need? We have to sum up those kind of the plan. Then the reviewers can judge it's realistic or not to achieve the good results. So depends. So long time ago for your sample, I've got 2 days for only one sample, one temperature. Because I appealed why we need such sort of super high statistics.
So in case we have a good reason to have much more bigger statistics. So it depends on the reviewer. Is it possible? Yeah. Okay. Thank you.
Okay. Thank you. Okay. Any other question? I also want to remind you that all the students have to fill the form, Google form for the absence, daftar hadir ya. Please fill the form. Okay. Any other questions? Or that was already 2.5 hour actually for the for the last session. Okay. Any other question or no? Okay. Okay. We will have a photo session for the end of this first lecture. Could you please open your camera just a moment or 3 or 5 seconds, please? We will have a photo session. Okay.
Suchi-san.
Yeah.
Suchi-san.
Yes.
New glass is good.
Okay. Rosaldi, Tri Joko Padadang, Vira Helma, Sarifa, oke, Dimas, Ulfa, Trisna, oke. Ini first screen, Budi, Utami, Eka, Abdan, Suci, Ruli, Rosaldi, Andri, Lutfi, Anissa, Bulusi, Patogar, Pak Rahman, Gita, Yati, Vira, Rosaila, Tri, Nabila, Trisna, Ulfa, Dimas, Saripat. Okay, this is the first slide. Okay, 1, 2, 3, smile. Okay, this is our first slide. Thank you very much. Okay, sorry, Ulfa, there is no Ulfa. Okay, another first slide. 1, 2, 3, 4. Okay, thank you for the second slide. I just took twice for each slide. Okay, for the second slide. Okay, Ilman, Jedija, Nabila, Gita, Helman, Nur, Hanifa, Lucia, you can. Okay, Jedija, Miri. Okay. Second slide, please. 1, 2, 3. Okay. 1, 2, 3. Okay. Okay, thank you very much, Watanabe-san. It's a very nice question, nice discussion. We already have a quite a long lecture today, 2.5 hours. Goes very fast because your presentation is very nice. Hopefully we can also get your lecture in the next 2 weeks for superconductivity and DFT yes, sorry, the FT.
First week is fine. First week is fine for me. First week of April. But next week a little bit
yeah, okay.
not so good now. Sorry about this.
Okay, so it's mean the 8th April, isn't it? 8 April. 8, yes. 8, is it okay?
Wait.
8, because next week, Tuesday is 1st April. It is hard for you. There are a lot of deadline, isn't it? So it's we will go for our second lecture for the FT and superconductivity. 8
Okay.
April.
Yes. Then time is
7:30 Indonesian time, 9:30 Japan Standard Time.
same.
Yes, same.
はい、ありがとう。
Thank you very much. Okay, thank you very much. Give a big applause to Dr. Watanabe. Thank you very much for sharing us, for giving us the very nice lecture. Hopefully,
You're welcome.
yes,
Sama-sama.
thank you very much. Hopefully, all of you have a good health and can be success for everything. Okay, I close this. Yes.
Can I talk with you a little bit after this?
Yes, of course, no problem. Yes, no problem. Yes, okay. I will close first the lecture. Okay. Thank you very much for your attending today for 2.5 hour. Hopefully you enjoyed the lecture and you get a lot of language, a lot of things from this lecture. Of course, about material science, about MUSR. We will have again a lecture in the next 2 weeks about superconductivity and DFT for computer simulation. And again, hopefully all of you always in the good health. I close the lecture with hamdalah, alhamdulillahirobbilalamin. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Thank you very much, Dr. Watanabe.
Thank you very much, Watanabe-san.
Thank you very much.
Bye-bye.
sama-samaバイバイ。
Bye, bye-bye.
Thank you, Watanabe-san.
バイバイ。はい、ありがとう。
Gado.
Gozaimasu.
Terima kasih.
I have a discussion with Dr. Watanabe just
Ya, simple one.
simple one. Pak Rahman, sebentar ya Pak ya. Nanti saya ada diskusi dengan Pak Watanabe sebentar.
Ya, silakan Pak. Saya keluar dulu Pak ya.
Ya,
Watanabe-san, o hisashiburi desu. O genki desu ka?
Are you?
Yeah.
Suji-san, did you
I'm fine. I'm sorry I couldn't attend from the first because I have a class till 9 o'clock. So I just listen to the end of a part of your lecture. Yeah.
No problem.
So is there any good news about the measurement about the beam time maybe?
Your beam time, I've got a strong notice from Rutherford. They cannot arrange. As long as I can go to Rutherford, I cannot go to Rutherford because, as I talked to you, they don't like the light experiment so much.
Yeah.
Because they have to manage all the experiment in remote conditions. So then, on the other hand, British people, they tends to save the how can I say, daily lives for any people. That means the Rutherford staff can work from 9 to 4 only. Then go back to have rest. So, but unfortunately, light experiment, nobody knows how to set up and how to carry out.
Yeah.
Then they declared, as long as I cannot be at Rutherford, the light experiment has to be postponed. But they can guarantee the to carry out again next time. Next time means long shutdown will be continuing until the summertime next year. Little bit shortened. So that means after that, you can give the priority on your experiment. Maybe next year I can come directly. Then we can carry out. But I'm sorry, we have to ask you to postpone at this moment.